Okay. Homework is due by 6 o'clock this afternoon. The new problem set came out yesterday. It is due Tuesday at 6 o'clock. Normally like 5 or 6 problems. That'll be. After today's lecture, you'll be ready for it. Today is the last lecture of new material in physics that you will ever have for the rest of your natural lives. Yes. Ever. I've made a decision, since it is my last semester teaching in this room forever. I know. I have a humble request. Next week, during the test, we're going to red out. I want everyone to wear red for the test. Now, what does that mean for you? What do I get? Well, I get my last request. What do you get the satisfaction of giving something back to me? And a generous curse. So everyone just wear bright, obnoxious red. I'll be posting emails to it or sending out further messages. And then what we'll do is, before the test, I'm going to take a few photos and maybe give a little motivational speech and take videos of it and post it on YouTube and become great. Yes? I'll do that. If you want to early. Okay. All right, fine. I can do that. Yes. Tomorrow will be a, now here's the deal. I just want to show of hands. Who intends on being at this tutorial tomorrow? 2:30. 1, 2, well, if I could just have, okay, all right, enough. Because if I can't do a tutorial to an empty room, I have to have people that I can bounce ideas off of. So 2:30 to 4, we'll have the tutorial. We'll do problems. We'll do test review. Next Tuesday is another test review. You guys love test reviews so much, we'll try to get all the Wednesday. While we're at it, I also went, just to say it again, copies of old test threes are out on Blackboard. Copies of previous finals are now posted to Blackboard. So you got everything that you need. So a bit of qualitative stuff initially. Today we're going to talk about thin films. As we've learned in Physics 2:13, if you have a wave and it hits another wave and they are both peaks, you get a bigger wave, and then they move away. This is constructive interference. Now, it can also be done with the divots or troughs or valleys, what you call them. You get a bigger valley and then the wave moves on. This can occur with waves of water. It can occur, as you've seen in well, for those of you who've had lab up through today, it can happen with light. You've seen what single and double slit diffraction looks like. That if you get a trough to trough or a peak to peak, these are the bright spots that we see on the screen in your lab. There's also destructive interference. Where if you have a peak and it's hitting a trough, for one brief moment, there's nothing there. And then the peak and the trough reappear. Now technically the light waves are still there, but they've just canceled each other out. To you, it's a dark spot. Light waves here, when peak to peak hits, that is, you could say, is the waves are in phase. Where the dark spots are, you could say that the waves are out of phase. So we need to introduce, or we need to revisit the ideas of constructive and destructive interference. What does constructive interference means in terms of what do you see? What do you see in terms of destructive interference, which means black, dark, no light? And we need to introduce a new topic. I've never been, well, let me show you. If you have let's say you had a tree and you fixed a rope to it and you whipped it such that a peak hit that tree hit the tree and the tree was attached to the rope and the end of the rope was fixed. What happens is if you send a peak on a rope to a fixed point, it will bounce back. But it will not bounce back as a peak, it will bounce back as a trough. So a peak will be turned into a trough. Or if you sent a trough, a peak would appear. And what we call this is 180-degree phase change. If you had, instead of a tree, you could, or in all of these, you could just say it's a pole. But let's say you had a pole with a hoop, and that hoop was allowed to freely move up and down. Probably the best way, if we're thinking of this and with gravity, we're looking down at it. And if you sent a peak at a hoop that is allowed to move from side to side, it would not bounce back as a trough, it would bounce back as a peak. And there would be 0-degree phase change, or no phase change. Now earlier, just a moment ago, I said I've never been satisfied with the explanation as to why. Typically in all the books that I've studied at your level, they just say, well, in this case, since it's fixed, it does a phase change. In this case, where it's allowed to move up and down freely, there is no phase change. And that's it. a lot of people like to know, well, why is this? And so the only way that I could do it, and I'm not going to tell you, I'm not going to show you the proof, because it would require you to have a junior level understanding of physics. Like you would have to be physics majors or engineering majors and have already taken through differential equations and some introductory major level courses. It's in the math. It is a mathematical requirement that in situations like this gets a phase change, that doesn't. Basically, the bottom line is, because I say so, a little bit more of an explanation, it's because the math says so. If you decide to become a BA physics major, you'll end up in a course where you'll figure this out. You'll do the equations. So, in light, if we say that the surface that it's bouncing off of is N2, so now we're taking this analogy and comparing it to how does light behave when it bounces off a surface. If the light is traveling through a surface whose index of refraction is N1 and it reflects off the surface whose index of refraction is N2, this is like N2 greater than N1. If the index of refraction of N2 is greater than N1, there will be a phase change of 180 degrees. So really what you're looking at is this thing bouncing off an index of refraction that is greater than or lower than the index of refraction I'm currently studying now? If N2 is less than N1, there will be no phase change. So a light wave is traveling through something and it hits something that has a higher index of refraction. It will bounce and be an inverted version of itself. If a light wave hits a surface and its index of refraction is lower than what it's traveling through, it will bounce back, but it will remain in its own phase. It will not change. Now, how I symbolically write this down, if you have N2 and N1, the light wave will come in and it will bounce off. If N2 is greater than N1, there is a phase change. And how I typically do it is at the contact point, I draw a filled in circle. Thank you for joining us, Sabrina. So now, don't look at her, she's self-conscious. If there is no phase change, in the case of N2 being less than N1, there's no phase change. and I just draw a circle not filled in. So there are no phase changes and there is phase changes. This is not in the book in terms of how I fill in the circles or don't, but it's a technique that I use in order to keep track of things. So let's get to what we really want to talk about, are thin films. Now, thin films, what's the best way to demonstrate thin films is to remind you of what you have seen in earlier situations. You're at a gas station. It had recently rained. Obviously, there's going to be gas and oil all over the place because it's a gas station. And there's a puddle. You look into the puddle and what do you see? You see bands of colors. You see blues and reds and greens, all sorts of colors. The gasoline you're up here in air, the gasoline is floating on the water. Another example of what a thin film is, you blow a soap bubble. Now this is highly exaggerated, but you have air on the inside of the bubble. Obviously there is air on the outside, and there is soap water in the middle. And what do you see when you look at a bubble? You see these weird, trippy bands of colors, drops of colors going through other bands of color. What this is, what you're seeing is constructive and destructive interference within a thin film. What is happening is light there are two places for the light to reflect off of. Light can reflect off the first interface. In this case, it's air to gas. In this case, it's air to soap. And then it reflects off the next surface, which is, in this case, gas to water. In this case, it is soap to air. And if, at the question mark, if those rays are in phase, peak to peak or trough to trough, constructive interference occurs, and you see that color. So if a green ray bounces off and another green ray penetrates and bounces off, if those two green rays are in phase, you see the color. So if those green rays bounce, and if this green ray is out of phase from that green ray, then what happens is they will destructively interfere with each other, and then you won't see it. If you're only using a single color, it would appear to you as if it was black, dark, no light. If it was a wide spectrum of colors and only green was destructively interfering, then you would see the light minus green. So just red and blues. So what happens is you will be given a set of situations where you have air, gas, water. Can't even spell water. How sad is that? Air is 1.0. This will all be given to you, or you have to figure it out. These are the indexes of refraction. And so how I occasionally draw this is that light will come in, it will reflect off that surface, it will reflect off that surface. Sometimes I draw it like this. This is also a good way. Remember, if the reflective substance has a higher N, there is a phase change. Really what's happening, when light hits a surface, some of the light reflects and some of it passes through.
Right, so it's reflected from the bottom and then it comes back through the top.
Yeah. Now,
it hits the bottom of the gas.
Yeah.
And it comes back from it's reflected.
The light, yeah, light rays are split off this surface.
Right.
And then light reflects off there. Now, granted, truth be told, some of the light continues on into the water.
Right, but the part that's reflected back up on that second one,
Yeah.
it's right there. Would it be split again?
Yes, it would. But the thing that we look at or most concerned with is, what do we see? Because the light that you are correct, this will reflect off of that. But it goes away. Also, every time it reflects off a surface or transmits through a surface, you're losing intensity. So eventually it gets faded. This is kind of related to why do we see rainbows? Because light, it gets bent through the bubble. Well, it's not constructive, that's diffraction. But in terms of using your example, light will constantly bounce around in that bubble. Hence, you see the primary rainbow, and then if you look a little bit away from it, you'll see a secondary rainbow. And what is that secondary rainbow? It is a much weaker rainbow because it's had to bounce off the surface multiple times, and with every multiple bounce, you're losing intensity. So low to high, low to high. This is an even situation. There are an even number of phase changes. Now we can have a situation where it is air, glass, air, where air to glass we're going up 1 to 1.5, but here we're going from 1.5 to 1, so there is not a phase change at the secondary interface. This means it has an odd number of phase changes. So that's an example of, you can have a situation where you'd have 2 phase changes. You can have a situation where there is 1 phase change. You can have a situation where there is, let's say we had a situation where it was like 1.5, 1.3, and 1.0. High to low, no phase change. High to low, no phase change. And so this we could say is an even number, because I treat 0 as an even. And you could even have a situation where, let's say, glass, air, glass, where this is an odd. So these are the 4 things that, well, the numbers would be different, but there are 4 possibilities. Either there are 2 phase changes, no phase change, and then 1 phase change, and that phase change could occur at the first or the second. When you, yes. The even number. Well, and this is 0 an even number? I'm not really buying it. But I would put 0 in the same category as this. Because if it goes from high to low, there's no phase change. High to low, there's no phase change again. So the total number of phase changes is 0. The one on the right, air, gas, air, there's a phase change at the first interface, but no change at the second, so there's 1. So you're either going to get 0, 1, or 2. So right now it's all qualitative. We're going to get to quantitative in a little bit. Yes? I'll have to remember. I'll accept it. I'll take 0 as 0 or even. Because really what there's happening, there's 2 equations that we're using. One is going to be the case of and of. The other equation is going to be for 0 or 2. So, if you want to call it even, 0, you could just, or we could say it's non-odd. Say, if there's 1, you use this equation. If there's not 1, you use the other. Is that the logic that we define? And what's really interesting is that I've taught this particular subject for like for like 3 to 4 years now, and I've never had the case where someone said, 0 isn't even. It's not odd. What is it? So, okay. The two types are 1 or not 1. So if there is one flip, do what? Two types. There are two types of problems that we're dealing with. God, you guys are picky. But then again, science is a picky material, so. So fine, I won't use, I'm probably still gonna use even in some respect. If there is an odd where there's only 1, because we can all agree 1 is an odd number. Odd students, odd numbers. There we go. What is important about this is to determine if it's destructive or constructive interference. It's dependent upon a couple of factors. One is you have to consider lambda, the wavelength of the light. You also have to consider which type of thin film are we dealing with? Are we dealing with where there's only 1 flip, or are we dealing where there's only 2 or none? And then what's also necessary is the N of the film. The index of refraction of the middle material. And lastly, the thickness of the film. Well, okay, well, are we looking for constructive or destructive? Because that'll also decide which equation we use. In situations where there's only 1 flip, a quantity that we must pay attention to is m lambda, where m is just an integer, and it's destructive, and then m plus 1/2 lambda is constructive. For the not ones, m lambda would be used in the equation if we're looking at constructive. And then m plus 1/2 lambda as destructive. So we have these situations.
How can you have constructive if you only have 1 phase change? Because you would have the peak going in and the peak coming out on 1, right?
Well, I'll use, well, what we're looking at, and I'm just going to use generic, the materials don't really matter. When the first light ray reflects, we're really interested in what's the phase of the light at the moment it reflects off the first surface. And then we compare it to well, we take a look at the phase of the light that has just reflected off that surface. And then compare it with the phase of the light coming out. So we look at the first ray and go, are you a peak, a trough, or somewhere in the middle? First wave goes, I'm a peak. And then the second wave comes out and goes, and I go, are you a peak or a trough, or somewhere in the middle? And it goes, well, I'm a peak too. So you've got peak reflecting, peak coming out, double peak constructed. If both of the phases are troughs, then it's constructive and you see light in that color. If the light here is a peak, and then the light, after passing through all of this and going through that phase change, if it comes out and says, I'm a trough, they cancel. Or if the other one is a trough and the other one is a peak. Remember, when light, as the light wave comes to you, it's going peak, trough, peak, trough, peak, trough. So this light ray, it makes it through the first boundary. And then it goes, well, I'm peak troughing in the middle of this thin film. Then I go through a reflection again. Oh my goodness, that's going to change the phase again, and or possibly. And then I'm going peak trough as I'm coming up. At what is my amplitude coming out of this wave? Am I peaking? Am I troughing? Am I somewhere in between? So you have to take into account the thickness of the material. The thicker the material, the more opportunities it has to go peak trough, peak trough. So for most colors, like if you have one thin film with a certain arrangement, typically the light coming through is kind of muddled and nothing really spikes up. But there's typically one frequency of light that is constructively interfering and it just glows. Such as when you look at a soap bubble, there are parts of the bubble which appear red. That means its thickness and the material arrangement is set up so that red constructively interferes. There are other regions where green constructively interferes. There are other regions where it's just kind of gray, and that's all the light coming through, so you're not really getting a clean signal. I wish I could have, like, eventually there's going to be augmented reality in physics classes so you can see the light waves. Like one light ray has bounced, this light ray has passed through all this material. The real question is, are they both peaking, are they both troughing, or are they peaking and troughing at the same time? And it's an interesting topic, and this pushes the boundaries of your visualization abilities, and I like that. The one thing I will say as advice the first time I ever taught this to a class, I admitted in the class I'd never taught this before, and that causes chaos. This is the third or fourth year I've taught it, so I'm a little bit better at communicating it. So in terms of the mercenary 214 student, what's in it for me? You gotta know, is there an odd or not odd phase change? Do I need constructive or destructive interference? What's the thickness of the film? What's the index of refraction of the film? And we can get some equations. So this lambda is based on the wavelength in the material. So the lambda that we're going to use, we'll call lambda prime, and it will be lambda over n. That lambda is wavelength in a vacuum, and n is obviously the index of refraction. And this is required because as it's passing through the material, its wavelength changes. So it may go peak trough every 2 meters, let's say, in air, but in the material, that wavelength will change to a different distance. So you have to take that into account. Now for the equations that we use, is 2t m lambda over n, and 2t equals m plus 1/2 lambda over n. So in the case of an odd, the destructive is m lambda over n is equal to 2t, and constructive is m plus 1/2 lambda over n is equal to 2t. For the not odds, the constructive will be m lambda over n is equal to 2t, and destructive will be m plus 1/2. That's a horrible E. Will be that. The T, great, now that is the thickness of the material. Now, why is it 2t? Well, it had to travel a distance 2t. So now, let's do a problem. Okay, let's do the air, gas, water. So air 1.0 index of refraction. Gas, 1.15. What, did I really measure the index of refraction of gasoline? No, I just chose the number. Call it rebellion gas. And then water, 1.33. So the first wave bounces. It goes from a lower to a higher index of refraction. Is there a phase change? Yes. Phase changes always occur when the reflective material has a higher index of refraction. So circle solid. Second wave bounces off water, from gas to water, lower to higher again. There is a phase change. And we have another. So this is definitely not odd. And let's say lambda, and this is one of the things where I think it is a valid question to ask, is when I say lambda and I give you a number, I have to be very specific. Is that lambda that I give you the wavelength in vacuum or the wavelength of the material inside? I will say most of the time, I'm very explicit in the problem sets, this lambda is in vacuum. So the lambda of the vacuum is 600 nanometers. That light constructively interferes. Because I say so. I will typically say, now let's go over problem solving technique. If I say constructively interfere, it is constructive interference. If I say that it has a high intense green hue to it, that's constructive. If I say there is no green there, it's destructive. If I say it appears dark, it's destructive. So understand the words that are associated with constructive and destructive. Yes. Light, yeah. What I mean by light, some people would associate with light green versus dark green. No, light as in green is there and you see it. Light and dark is how I typically associate with light bands and dark bands. Dark bands, destructive interference, black, no light getting through. Constructive, light, shining, stuff like that. So what we look at is, this is a not odd constructive interference situation. Not odd constructive interference, and we write that down. I'm looking for minimum thickness. Okay, now here's another well, is it common sense? Is it problem solving? Perhaps either. Perhaps both. If I'm looking for the minimum thickness of this thing, what is the M value I'm looking for? What is the M that I associate with the minimum thickness? 1. She's right, you're wrong. If M was 0, Well, you were right, and now you're wrong. Forever. If you chose m as 0, the thickness would be 0. How can you have something with thickness if its thickness is actually 0? It's non-existent. So in situations where you have m and not m plus 1/2, the smallest number you're allowed to use is 1. If we had, say I chose destructive interference for it not odd, I would use the m plus 1/2 equation. Now, the smallest m that I can use is 0. Because 0 plus 1/2 gives me 1/2, and we have a non-zero thickness associated. That moment, oh, processing, okay.
Processing. You specify the thickness.
I will either, well, in this case, I'm asking for the thickness. There could be situations where I give you the thickness and say, would green light of this wavelength constructively or destructively interfere? M stands for what order? It's just an integer which will give you it's an integer used that will allow you to set working values of thickness with wavelength and stuff like that. Yes? We're solving I kept the light wavelength in nanometers because the answer that I want should be, the thickness should be in nanometers. So 600 divided by 2.3, and yes, you always use the index of refraction in the middle because the light, the second ray, the ray that's passing through the film, that's the thing that's actually going up, down, up, down. It needs to know how many times it goes up, down, up, down. And the only way that you can do it is to know its wavelength within the material. So 261 nanometers. What? The thickness. As I've said before. So really, it sounds very, the conceptualization of how these types of problems work is kind of high in terms of visualizing what's going on. Its application is actually pretty simple. You identify, is it odd or not odd? Is it constructive or destructive? It's a lot like like capacitor, series or parallel with resistors, series or parallel. You go, am I dealing with capacitors or resistors? And are the resistors in series or in parallel? And then you get the right equation that you need. Or it's a lot like Doppler shifting. Is it a moving source or a moving observer? Is it heading at me or away from me? And then you use the proper equation. So the one last thing that and it's such a bear to do because I need numbers that actually make sense. All right, so the one last thing, we'll do one last example and then we're out. In the tutorial tomorrow, there's a particular problem on that problem set, I think, that will fry your brains. It's a test grade problem. Look at it and then tomorrow we'll discuss it. All right, since we did not odd, we'll do odd. Oh, okay. Reminding you when and where? All right, hold on. And we will have tutorial because baseball game doesn't start until like 7. So 6:30? Oh, that's plenty of time. All right, now we're gonna go with an odd. If you look at, they're called Newton's rings. You have glass, air, and glass, and they're typically at an angle because what happens is you can take a screw and screw down the upper plate and it changes the distance. But the only thing we're really interested in is glass, air, glass. Index of refraction of glass we'll set at 1.5, 1.0, 1.5. We have the added benefit of knowing that air is index of refraction is 1, so we don't have to deal with that time bomb of knowing what lambda is in the material, because the lambda that I give you is it. I want to do something. So this is odd because glass to air is a lower, no phase change. Air to glass is a higher, there is a phase change. So we will get constructive for this and destructive with that. Now, give me the smallest thickness where 550 nanometer light is highly visible. Excuse me? Yes. That's what we call it. So if it's highly visible, it's bright. Bright implies constructive interference. It's an odd situation, so we use m plus 1/2 lambda over n equals 2t. In physics 214, index of refraction of air is 1, not 1.000001 like those dopes over in the lab think. As far as I'm concerned, it's 1. So to get the smallest thickness, m must equal 0. And I'm left with lambda over 2 is equal to 2t. N is 1. Yes. Is what? No. Remember what equation we're using. M plus 1/2. 1 plus 1/2 or 0 plus 1/2? 0 plus 1/2. So it depends on, the minimum integer is dependent upon which equation you use. So 550 divided by 4, or 137.5 nanometers. Did I do the math right? Yeah, okay. So on the problem set on Blackboard, there's like 5 to 7 problems. All they're about is they give you the materials that you're traveling through. They tell you if the light is constructively or destructively interfering. Then you have to find either lambda or the thickness or something. There's one problem that's a little bit torturous, and I'm going to go over that tomorrow afternoon. I'll email reminders soon. That's it.